I know how much you love talking about mechanism. So I want to look at the mechanisms that we have when we consider either the making or the breaking of this ester linkage. Okay, so when we are making esters, right, we are generally going to be talking about having a carboxylic acid functional group. Remember that carboxylic acid is going to be coming from our fatty acid, and we are going to be combining that with an alcohol. And that alcohol is going to come from our glycerol backbone. Okay, so this is often referred to as Fischer esterification, but I want to walk through the mechanism of how this happens. So remember, anytime you are looking at a mechanism and you are seeing a new bond that is forming, you want to ask the question, somebody came to that new bond with electrons, so they were the nucleophile, and then somebody received those electrons. They were the electrophile. So if I look at what I have here, and I can already see from my arrows that are drawn, I've got my alcohol here that is going to be the nucleophile. Nucleophiles are generally going to have heteroatoms like nitrogen or oxygen with lone pairs of electrons. Very rarely will we see carbon atoms that are going to be nucleophiles, but we have seen it when we talk about deprotonating the alpha carbon that allows us to generate an enolate. Okay, but what we have here is alcohols that are not great nucleophiles. So what we can do is we can make our electrophile more electrophilic by protonating it, giving it that positive charge. So now this protonated carboxylic acid is much more electrophilic. Nucleophilic attack by our alcohol here generates a tetrahedral intermediate. Now in this case, we want to have a leaving group leave, so we want that OH group from our carboxylic acid to leave. Theme that we see is if you protonate leaving groups, it makes them more able to leave here. We're going to deprotonate our incoming nucleophile here because we don't want that to be a good leaving group. We sort of get back here to, and I am missing here, we are missing our OR group here. Okay, so if we want then to decompose this tetrahedral intermediate here, we can decompose this tetrahedral intermediate. Leaving group can leave. We protonated our OH group, so now that's the good leaving group, and we end up with a protonated ester. Deprotonation of that generates our ester. So that's how we are going to be making our ester linkage here. Here you can see this is why this is a condensation reaction. Condensation reaction here because we have eliminated water. So there's the water that we eliminated. So again, this is why this is a condensation reaction. Okay, that was how I'm going to attach my finger, fatty acid with its carboxylic acid functional group, onto the alcohol group that is part of my glycerol backbone. All right, so let's look now on how we can hydrolyze that or break that linkage. We can break that linkage in one of two ways. Ester hydrolysis can either be acid catalyzed or base promoted. So let's take here, the top part is going to look at our acid catalyzed fashion. In this case, we're going to have hydrolysis. We want water to act as a nucleophile. Water is going to be not a great nucleophile. So again, how do we make something be a better electrophile? We protonate it. So protonation of this ester is going to generate a protonated ester, better electrophile for nucleophilic attack by water. Generate a tetrahedral intermediate. In this case, we need to do some proton rearranging, so we make the leaving group that we want to leave, the alcohol there, be protonated, and our incoming nucleophile gets deprotonated. If we don't do that proton rearranging, we are going to end up having the wrong leaving group, right? We don't want our incoming nucleophile to be the best leaving group. So proton rearrangement here is going to generate a tetrahedral intermediate. Now that when it decomposes, departs the leaving group that we want to depart, and we get back to, in this case, if we're talking about hydrolyzing our triglycerides, that will be how we get our glycerol backbone back. And then here we end up with the carboxylic acid, protonated carboxylic acid that we have there. Okay, and so when we deprotonate that carboxylic acid, we get back to our carboxylic acid. That would again be our fatty acid. But note here, we say that this is acid catalyzed because the acid that we use there in the beginning, we regenerate at the end. So this is why this is called acid catalyzed. Note the difference when we look at the mechanism here for down here, this is what we call base promoted. It's not base catalyzed. We don't regenerate the base catalyst. This reaction is promoted because in using hydroxide, we use a better nucleophile. So we are going to be able to better react with that electrophilic carbonyl. Note here, I could not start with this material down here. There is never a pH environment that will be acidic enough where I can protonate my ester, but also basic enough to generate hydroxide. You need to think about what your pH is, and that will determine the protonation state that you can have of your molecules. So in this case, base promoted facilitates this reaction by making a better nucleophile. Nucleophilic attack here on my ester generates a tetrahedral intermediate. I really don't need to do proton rearranging here because I don't need to deprotonate my incoming nucleophile. It already was deprotonated. And then in this environment, I can likely just have my alkoxide group leave. And so in this case, I'll generate these intermediates that probably will reshuffle their protons afterwards. And that if I look at the pKa values, a carboxylic acid with a pKa of 3 to 5 is much more likely to be deprotonated. And my alkoxide, which again is the deprotonated form of an alcohol with a pKa of 15 to 16, is much more likely to be found in its protonated form. So a little bit of proton rearranging ends up with these species that are likely in their proper protonation state. Again, we still would have, this would be if we are hydrolyzing our esters that were our linkages in our triglyceride, we'd end up with glycerol, and then we'd end up with our fatty acid. All right, so a little bit of mechanism there to think about for triglycerides, the ester formation or condensation or breaking or hydrolysis chemistries.